Hello, and welcome to 123 AP Physics with Zach Speaks the Science Geek. This week we're going to be talking about work, energy, and gravity. So, what is work? Work is the change in an energy of a system. So, the formula for it would be the force times the displacement times the cosine of the angle between the two, which is the dot product of the force and the displacement, and work's measured in joules, as is energy. And so energy is the ability to do work. So that sounds kind of circular, but it will make sense later on. So there's two main types of energy. There's kinetic energy, which is energy due to motion, and potential energy, which is energy due to position. So types of kinetic energy would be, there's only one that we will need currently, and that's just translational kinetic energy. So that's 1/2 times the mass of the object times the translational velocity of the object. And then potential energy, there's spring potential energy, which is 1/2 times the spring constant of the spring K, and the displacement the spring undergoes squared. And then there's the gravitational potential energy, which is the mass of an object times the gravity times the height of the object above the ground, measured in meters. So conservation of energy. So work is the change in energy. So if there's no change in energy, then the beginning and ending energies are the same, and we can use that to simplify solving a lot of equations and make our lives a lot easier. So gravity. So the force of gravity is equal to the gravitational constant G, which is about 6.67 times 10 to the negative 11th, times the mass of the first object times the mass of the second object divided by the distance between the two objects squared. And so because that gravitational constant G is so small, you need very large masses to have a significant amount of gravity. So you'd, like, if you used Earth or if you used the sun, then you would actually get a large number. If you used Earth and the radius of Earth for r, you'd actually get 9.80 once you've divided by the mass of the object you're calculating the force of gravity for. So here's our first problem. A 20 Newton force acts on an object for 5 meters at an angle of 45 degrees to the horizontal. What is the work done by the force? So we're just going to plug these into our formula. So it's 20 newtons times by 5 meters times the cosine of 45 degrees, which is about 70.7 joules. Next problem. A 10 kilogram box falls from a 10 meter high window. What speed is the box traveling at when it hits the ground? No non-conservative forces act on the box. Solve with energy. So before we'd solve this with kinematics, and we'd say 10 meters is the displacement, and the acceleration due to gravity is 9.80, and the initial velocity is 0, and the final velocity is what we want to find. But now we have a lot shorter way. So now we can just use 1/2 mv squared is equal to mgh. So this is the final energy right here, and this is the beginning energy, because there's no non-conservative forces acting on the box. So energy is conserved, so we can just set the initial energy equal to the final energy and solve for our unknown value. So 9.80 meters per second squared times by 10 kilograms is equal to 10 meters rather, my bad, is equal to 0.5 times the velocity squared, because the m canceled on both sides. So we'd simplify this equation, and we'd say that the velocity is equal to the square root of 196, which is 14 meters per second. So the box would be traveling at 14 meters per second when it hit the ground. And so you should get the same answer if you solve this with kinematics, and you know that it's independent of the mass of the box because the mass canceled out on both sides. So the box could weigh 0.1 kilograms, it could weigh 300 kilograms. It's still going to be traveling at 14 meters per second when it hits the ground. So problem 3. A spring with constant 2,000 and 2,540 newtons per meter is compressed by 0.5 meters and then connected to a 15 kilogram block. what speed is the block traveling at when the spring is no longer compressed? So this would be when there's no spring potential energy and it's all kinetic energy. So we set the initial spring potential to the final kinetic and say that 1/2 k delta x squared is equal to 1/2 mv squared. So 2,540 newtons per meter times by 0.5 meters squared is equal to 15 kilograms times the velocity squared. And solving for velocity, we would get that the velocity is about 6.5 meters per second. Pretty simple problem. If you noticed, so far all the problems have been roughly the same. You just have different initial and final quantities and you're just solving for the same thing. And so that's why this lesson is going to be pretty short, because with energy it's really the same thing over and over and over. There's different initial, different finals, but you're always going to use the same approach to the problem. So next problem. A 10 kilogram box begins traveling along a level table for 5 meters at an original speed of 7 meters per second. If the coefficient of friction is 0.4 for the table, what is the work done by friction, and what is the final speed of the box? So here we would say that the work done, first we find the normal force, and from it the frictional force. The frictional force is about 39.2 newtons. And then we'd calculate the work done to friction by multiplying by the displacement. And see, here we multiply by a cosine of 180 because friction is in the opposite direction of the displacement. So that would produce a negative work value. You're losing energy due to friction, and thus your final speed is going to be less than your initial speed. So we'd say that work is equal to change in energy, and we'd say that the final speed is equal to the initial speed minus the energy loss due to friction. Solving for V, we would get that V is about 3.1 meters per second. So you see that it over halved its speed due to this. And yeah, so friction halved its speed in just 5 meters. So that's pretty impressive. A spring with constant 1,450 newtons per meter is directed upwards and then compressed 0.37 meters. So we got a spring sticking up in the air and it's compressed 0.37 meters. And a 5 kilogram ball is placed on it and the spring is then released. And so what is the maximum height obtained by the ball and the maximum speed that the ball obtains? So for the maximum height, we'd say that all the energy has been converted from spring to kinetic back into potential energy, except now it's gravitational potential energy. And so we'd set spring potential energy equal to gravitational potential energy and solve for the height, and we'd get 2 meters. And then for the maximum speed, we'd say that all the spring potential energy has been converted into kinetic energy, and so we'd set spring equal to kinetic, solving for V, and we would get that V is about 6.3 meters per second. Next problem is going to be our one and only gravity problem. Gravity problems, they're all going to follow the same formula. You plug in the numbers, and what's the result? That's going to be every single gravity problem. That's pretty much the only thing you can do with gravity. You could ask how gravity decreases as radius increases, or not radius, but rather the displacement between the two objects increases. But again, it would just be, you could plug in bigger numbers for the displacement and you'd see that gravity decreases as a square. Okay, so G times by 35 kilograms times by 20 kilograms divided by 0.1 meters squared. We'd plug in what we know for, and we'd get that. So we've plugged in everything, and now we just simplify the equation. You get that the force due to gravity is 4.7 times 10 to the negative 6 newtons, which is actually very small, and that actually makes sense because, as we said earlier, you need really, really big masses, like 10 to the 30th masses, to get a sizable gravitational attraction, because that G constant has a 10 to the negative 11th in it. So it's very, very small. So 35 and 20 divided by 0.1, it's not going to pull you out of that big hole that G, the gravitational constant, is getting you. Okay, so let's start working on our FRQ. So this lesson's been pretty short. My college classes have started, so I'm getting a lot busier, so the other lessons will be short. The last really big lesson we have is circles, and in that lesson, that's 2 weeks from now. In that lesson, we're gonna be covering circular forces, circular momentum, energy, rotational kinematics, rotational dynamics. We're going to be covering everything that you see about circles in that one lesson. So it's going to be a long lesson, but all other lessons should be short. I'm trying to keep them under 20 minutes a lesson. So let's start working on the FRQ. Pause the video if you want. Start working through it. I'm going to start reading it and explaining it in 3, 2, 1. Okay, so I got this FRQ from the 2013 College Board, and I had to modify it because some of it was talking about simple harmonic motion, which we haven't learned yet. So a 20 kilogram box is on a horizontal frictionless surface is moving towards the right at a speed of 4.0 meters per second. The box hits and remains attached to one end of a spring of negligible mass whose other end is attached to a wall. As a result, the spring compresses a maximum distance of 0.5 meters, and the box then oscillates back and forth. We're going to ignore the box then oscillates back and forth because we're not going to be doing anything with it. The spring does work on the box. From the moment the box first hits the spring to the moment the spring first reaches its maximum compression. That got cut off pretty badly. That should indicate if the work done on the box was positive, negative, or neither, and then justify your answer. And then calculate the magnitude of the work described in part 1, and then calculate the spring constant of this spring. So, alright, I'm going to start working on the solutions now. So for A, it says the spring does work on the box, right? So the spring's going to be slowing the box down, right? The box has kinetic energy, and the spring slowing the box down, so it's losing that energy. So the if work equals the change in energy, if the change in energy is negative, then the work is negative. So we would say that the box is slowed down by the spring, reducing its kinetic energy. Therefore, the work done on the box by the spring is negative. And then to calculate it, we'd find the initial kinetic energy of the box, and since it's all turned into spring energy in the end, we could just say that that's the amount of spring energy at the end. And that's the amount of work done, because the work converted all that kinetic energy into spring potential. So we'd say that 1/2 times by 20 kilograms times by 4 meters per second squared is equal to the work, because the box is motionless at the point of full compression, meaning there's no final kinetic energy you have to worry about. So plugging in and simplifying, we'd say that 160 joules of work were done. Moving on to the last part, we would say that 160 joules is equal to 1/2 times K times 0.5 meters squared, because we're solving for K. Calculate the spring constant of the spring. So we're solving for K, and so since we know the amount of energy, we know the compression, we know that half constant, so we're just solving for the spring, and we could simplify it and just say that it is 1280 newtons per meter. That's all for this week. It's a short lesson, as I said. If you need practice, rewatch portions of the video, change the numbers, and you can always search for more College Board FRQs if you want to work on those, or search for physics, energy problems, and there are tons out there. So see you next week.